Welcome to the deep dive. We have a topic on the table today that, honestly, it sounds like a premise ripped straight out of a science fiction novel.
It really does.
But it is completely grounded in actual, verifiable mathematics and theoretical physics. I want you to start by asking yourself a question, and it's a bit of a mind-bending one.
For sure.
What if the greatest mathematical genius of the 20th century wasn't actually doing step-by-step math in his head?
Right.
What if instead he was somehow directly perceiving the hidden geometric source code of reality?
It is a really profound question to start with. And if the sources we're looking at today are correct, the answer completely changes how we look at the history of human cognition.
Yeah.
It changes the nature of mathematics and really the fundamental architecture of the physical universe itself.
Today we are exploring a fascinating 2026 briefing document and a deeply comprehensive paper. It's by Philip Lilien.
Yeah.
The paper is titled Srinivasa Ramanujan and the Ontology of Modular Structure: Coherence, Moonshine, and the Emergence of 24.
Quite a title.
It's a mouthful. And alongside that paper, we have a couple of highly detailed infographics that attempt to, well, they try to map out Ramanujan's mind.
Which is no small task.
No, not at all. And the incredibly specific mathematical landscapes he explored. Our mission for this deep dive is to completely rewire how you understand mathematical genius.
That's the goal.
We want to move past this popular, almost mythical narrative of Ramanujan as just some sort of like a human calculator.
Right, or a savant who simply crunched massive numbers in his sleep.
Exactly. We are going to explore what this paper calls the structural regime he accessed. It's a place where geometry creates symmetry, and that symmetry literally dictates the laws of physics. Okay, let's unpack this.
To really appreciate what Lilien's paper is arguing, I think we first have to take a step back.
Okay.
We need to look at how mathematics is traditionally done. Let's think about the vast majority of mathematicians throughout history. The process it's almost entirely procedural.
Linear.
Exactly, linear. You start with an axiom.
Which is a universally accepted basic truth, right?
Right. A starting point. From that axiom, you derive a lemma.
A stepping stone.
Yes, a minor proven proposition used as a building block.
Yeah.
And then, by stacking those lemmas together through rigorous step-by-step logical deduction, you finally arrive at a theorem.
So it is very much a structural build, axiom to lemma to theorem.
Brick by brick.
It's exactly how we are all taught to do proofs in high school geometry. You have to show your work at every single stage.
Otherwise, the conclusion isn't valid.
Right.
And the central thesis of these sources is that Srinivasa Ramanujan simply did not operate that way.
At all.
Not at all. His cognition functioned via what the paper formally calls global structure perception.
Global structure perception.
Instead of building the mathematical house brick by brick from the ground up, his mind seemed to start with the completed architecture of the entire structure already in view.
He just saw the whole building.
He perceived the whole shape of the math, and then he simply extracted the specific relationships and formulas from it. The paper describes him as possessing an intuitive compression engine in his mind.
A compression engine.
He recognized massive global transformation structures long before the formal procedural proofs for those structures were ever invented by anyone else.
I want to spend a minute on the historical context of this because it helps frame just how jarring his mind was to the academic establishment.
Oh, it was a massive shock.
When Ramanujan, who was largely self-taught and working as a clerk in India,
Right.
when he sent his notebooks to G.H. Hardy at Cambridge University in 1913, Hardy was completely floored.
He had no idea what he was looking at initially.
He was looking at these incredibly complex infinite series and continuous fractions that had absolutely no proofs attached to them, just the answer.
Just the raw results.
Hardy actually created a subjective scale of mathematical genius later on just to try and quantify the phenomenon he was dealing with.
It's a great scale.
On a scale of 0 to 100, Hardy rated an ordinary working mathematician a 25. He gave his brilliant collaborator, J.E. Littlewood, a 30. He gave David Hilbert, who was one of the undisputed giants of mathematics at the time, an 80.
A legend, yeah.
And he gave Ramanujan 100.
It is a telling scale.
Yeah.
Hardy famously noted that to Ramanujan, every positive integer was one of his personal friends.
Personals?
He had an intimacy with the mathematical landscape that defied standard logical progression.
That quote has always stood out to me. It sounds poetic, but based on what we're reading in this 2026 briefing, it might have been quite literal.
Very literal.
How does the concept of ontological mathematics, which is introduced in the paper, how does that help us understand that intimacy?
That concept is really the philosophical backbone of our sources today. It challenges how you, the listener, might normally view reality and the abstract world of numbers.
Okay.
In the framework of ontological mathematics, Ramanujan didn't view mathematics as a symbolic game invented by the human mind to describe things.
Not just a language.
Right. He treated mathematical relationships as existing fundamental realities. They are ontological facts.
They are actual things.
They exist independently of us, waiting to be discovered rather than being tools we invent.
So it's the difference between inventing a new type of hammer versus discovering a new mountain range that was already there.
That is a perfect way to look at it. And the sources introduce a core framework to explain this, which they call the ontological pipeline.
The ontological pipeline.
It consists of 3 distinct layers.
Which are
coherence, which leads to symmetry, which then leads to law.
coherence to symmetry to law.
Exactly. And the paper argues that Ramanujan was plucking his famous formulas directly from that final law layer.
Let's break those layers down a bit for the listener. What exactly lives in the law layer?
The law layer contains the explicit written identities. It contains the numerical sequences, the equations, the tangible formulas that Ramanujan mailed to Cambridge.
The actual math on the page?
Yes. But the critical point is that those laws are not the bottom of the reality well.
Okay.
They're just a downstream, localized expression of a much deeper underlying symmetry.
So law comes from symmetry.
Right. Think of symmetry as the governing rules of transformation. How things can move and shift while maintaining their core identity.
And where does the symmetry come from?
That symmetry, in turn, emerges from an even deeper foundational layer called coherence.
Coherence.
Coherence is the ultimate underlying geometric substrate. It is the raw, unblemished potential of mathematical space.
I want to try and give you, the listener, a visual analogy for this pipeline. Imagine the pursuit of mathematics like the exploration of physical geography.
I like this analogy.
Most brilliant mathematicians of the early 20th century were walking through a dense forest. They were meticulously mapping it, tree by tree, path by path, procedural step by procedural step.
Very grounded.
Ramanujan wasn't in the forest at all. He was looking at a satellite map of the entire continent from space.
He had the macro view.
He was sketching out the massive rivers and mountain ranges, the global structures, before anyone else on the ground even knew those vast landscapes existed.
And the specific mathematical landscape Ramanujan was looking at from his vantage point is what modern mathematicians call the modular surface.
The modular surface.
Which brings us to the geometry of constraint, a major focus of Lilien's paper.
The briefing document spends a lot of time on this. It dives heavily into modular symmetry, modular forms, and things called Q-series.
Heavy mathematical lifting here.
It is. I want to make sure we don't lose anyone here because it sounds incredibly dense. But the key takeaway seems to be that the equations Ramanujan was writing down weren't just arbitrary, random strings of numbers.
They were the exact opposite of arbitrary. They are incredibly special mathematical objects. Modular functions are globally constrained.
Globally constrained. What does that mean in practice?
To understand what that means, you have to look at how they behave under transformations. Let's imagine a complex parameter, a variable that exists on the complex plane.
Which includes both real and imaginary numbers.
Right. Mathematicians usually call this parameter tau.
Okay, so tau is just our variable living in this complex mathematical space.
Yes. Now, imagine applying a transformation to tau. For example, what happens if you shift tau by adding a whole number to it?
Just a simple shift.
Or, more drastically, what happens if you take tau and transform it into -1 divided by tau?
So you are essentially inverting it and flipping it.
Exactly. A true modular function is an equation that, despite these massive, sweeping transformations to its underlying variable, manages to maintain its essential core structure.
It survives the flip.
It might scale or shift in a predictable way, but its identity remains intact. That is an intense global constraint.
So the function is locked into this highly specific behavior. If you twist the space it lives in, the function has to twist in a very specific way to survive.
Precisely. And the consequence of that is profound. Once you force a mathematical function to obey these massive, overarching global symmetries, its local details, the tiny specific coefficients and numbers that make up the equation, become incredibly rigid.
Highly predictable. If the global rule is absolute, the tiny local details have no choice but to fall in line perfectly. They are constrained by the macro structure.
That is the essence of modularity. And the reason this constraint happens is deeply rooted in the shape of the space itself, which is hyperbolic geometry.
Hyperbolic geometry.
The sources take us deep into the architecture of the modular surface, explaining that it is a hyperbolic space.
I need you to help me visualize hyperbolic space because when I think of geometry, I just think of flat paper, straight lines, and standard triangles.
Standard flat geometry is Euclidean space. Hyperbolic space is negatively curved.
Negatively curved.
Instead of being flat like a piece of paper or positively curved like the surface of a sphere, hyperbolic space curves outward and away from itself,
Like a saddle.
somewhat like the shape of a saddle or a Pringles potato chip.
Oh, okay, I can picture that.
If you've ever looked at those famous artworks by M.C. Escher, particularly the circle limit woodcuts, where bats or fish interlock and seem to get infinitely smaller as they reach the edge of a circle,
Oh, yeah. I know exactly what you're talking about.
that is a visual representation of hyperbolic space. The space stretches out to infinity within a bounded boundary.
Okay, I have that Escher image in my head. How does that connect to Ramanujan's equations?
The paper explains that this entire infinite mathematical landscape of the modular surface is generated by one fundamental repeating building block.
A building block.
It is a specific hyperbolic triangle. It's known as the 2-3 infinity triangle.
The 2-3 infinity triangle. The paper basically refers to this as the DNA of the modular surface.
Yes.
Break down what those numbers mean in a geometric sense.
They represent the angles of this fundamental triangle.
Okay.
But in hyperbolic space, angles relate directly to symmetry and rotation.
Okay.
The first angle is pi over 2. In terms of symmetry, pi over 2 corresponds to an order 2 operation, which is a 180-degree rotation.
A half turn.
A half turn. The second angle is pi over 3. That corresponds to an order 3 symmetry, which is a 120-degree rotation.
A third of a turn.
Right. And the final angle is 0. In hyperbolic geometry, a 0 angle means the vertices of the triangle never actually meet. They stretch out parallel to each other forever.
Forever.
This is called the cusp, stretching to infinity.
I had a massive aha moment reading this section of the briefing, because when you look at Ramanujan's seemingly magical identities, these pages and pages of complex fractions and infinite series, the constants pi, 2, and 3 appear over and over again.
Constantly.
They show up in places that seem completely illogical for standard arithmetic, but they aren't random numbers.
They aren't random at all. They are the geometric DNA of that fundamental modular triangle.
It's just incredible.
Ramanujan wasn't doing arithmetic. He was pulling the literal geometry of the hyperbolic triangle directly into his algebraic equations.
Huh.
The numbers pi, 2, and 3 are the footprint of the space he was perceiving.
Can we look at a concrete example of this footprint? The sources point specifically to his work on partition functions as the ultimate proof of this geometric connection.
It is arguably his most famous work, alongside Hardy.
Let's quickly define partition so everyone is on the same page.
Yeah.
A partition function is a concept from number theory.
Very classic number theory.
It simply counts the number of ways you can break down a whole integer into a sum of smaller positive integers.
Right.
So if we take the number 4, the partitions are the number 4 itself, then 3 plus 1, then 2 plus 2, then 2 plus 1 plus 1, and finally 1 plus 1 plus 1 plus 1.
That's all of them.
That's a total of 5 different ways to build the number 4. So we say the partition of 4 is 5. It seems like a very simple, almost trivial counting game.
It does seem trivial for small numbers. But as the target number grows, the number of partitions explodes massively.
How massively?
Well, the partition of 10 is 42. By the time you get to the number 100, the partition is over 190 million.
Wow.
By the time you get to 200, it's nearly 4 trillion.
That escalated quickly.
Exactly. Mathematicians for centuries had no way to calculate these larger partitions without manually counting them, which obviously becomes impossible.
Right, you can't just write out 4 trillion combinations.
Ramanujan, along with Hardy, developed an astonishing asymptotic formula to estimate the growth of this partition function.
And what does that formula look like?
The Hardy-Ramanujan formula reveals that as the number, let's call it n, gets larger, the number of partitions grows at a rate proportional to the exponential of pi, multiplied by the square root of 2 times n divided by 3.
And there they are, pi, 2, and 3.
The exact DNA.
The exact DNA of the modular triangle. But there is a specific piece of that formula the paper fixates on. Why is there a square root of n sitting up there in the exponent?
That is the crucial question. For decades, it was just accepted as the way the math worked out. It just was what it was.
Right.
But the source material makes a compelling ontological argument.
Yeah.
That square root is not some random combinatorial accident. It is a direct, unavoidable consequence of the hyperbolic geometry we were just talking about.
How so?
In a negatively curved hyperbolic space, the area of a circle doesn't grow based on the square of the radius like it does on flat paper. Because the space is curving away from itself, the area grows exponentially.
So the space itself is getting larger the further out you go, like a massive trumpet bell or a funnel.
Yes. The square root of n in Ramanujan's formula is the exact mathematical footprint of that hyperbolic area growth.
That is almost spooky to think about. He was sitting at a desk counting how many ways you can add whole numbers together. But what his mind was actually doing was tracing the expanding surface area of a curved hyperbolic funnel in a completely different conceptual dimension.
It demonstrates that his intuition was not arithmetical. It was structurally bound to the geometry. He felt the curve of the space, and the formula was just the shadow that curve cast onto the paper.
Just a shadow.
This perfectly sets up the broader conceptual framework the paper proposes to explain how this geometric structure gives rise to the physical laws of reality.
Right.
It's called the meta-operator framework.
I want to spend some time here because this is where the paper transitions from pure math into something that almost sounds like the philosophy of physics.
It's deep.
The core idea they present is that symmetry plus asymmetry equals reality. How does this meta-operator actually work?
If we connect this to the bigger picture, the meta-operator is presented as the underlying engine of existence. It governs how reality emerges through the constant interaction of two opposing actions.
Two actions.
First, there is symmetry, which the paper labels as the S action. The role of symmetry is to regularize a state.
Regularize it.
It pulls chaotic or complex systems toward greater coherence, simplicity, and stability.
But if everything was perfectly symmetrical, nothing would ever happen, right? The universe would just be a blank, featureless void.
Exactly. Pure symmetry is completely static. It is a mirror, perfectly reflecting a mirror. So to get a functional, observable universe, you need the second component.
The A action.
The asymmetry action, or A. The role of asymmetry is to generate structured deviation. It breaks the perfect mirror.
It messes things up, but in a structured way.
Yes, it differentiates things, creating bumps, curves, and localized phenomena. The meta-operator, denoted as M, is the regulated dynamic interaction of these two forces. S tries to perfect the system, and A tries to deform it.
I'm trying to connect this to the physical world we actually live in. Does modern science view the universe this way, or is this just a neat mathematical philosophy?
Modern theoretical physics views the universe exactly this way.
Really?
The entire standard model of particle physics, which is the reigning theory of everything we can see and touch, is fundamentally based on this exact dynamic.
How does that work?
Physicists believe that at the very beginning of the universe, everything was perfectly symmetrical. All the fundamental forces were united into one perfectly coherent state.
Right, the Big Bang.
But as the universe cooled, that perfect symmetry underwent what is called spontaneous symmetry breaking. That asymmetrical breaking is what separated the electromagnetic force from the nuclear forces, and it is what gave particles their mass.
Wow.
Everything observable in reality is the result of perfect symmetry being slightly broken.
So the argument Lilien is making is that Ramanujan, by exploring these massive, globally constrained mathematical structures, was actually tapping into the literal generative mechanics of the universe.
That's the core argument.
To explain how this works mathematically, the paper dives into some deep geometric algebra. It specifically looks at something called a dual bivector triplet.
Yes.
So definitely need you to translate that into something I can visualize.
It is a dense term. Let's build a mental model. Imagine three distinct relational directions in space. Think of them as three distinct interaction channels, or axes, all converging at a single point.
Like three spokes on a wheel?
Similar to that, yes. Now think about the mathematical act of permuting or swapping these three channels.
Okay.
If you have channel A, B, and C, you could swap A and B. Or you could rotate all three, so A goes to B goes to C, and C goes to A.
Just mixing them around.
The mathematics of swapping these three objects naturally generates a very specific foundational symmetry group known in abstract algebra as the symmetric group on three objects, or S3.
Okay, S3 symmetry. And the paper makes a huge deal about this specific symmetry group because of the operations that govern it. Let me see if I'm following this.
Okay.
Swapping just two channels back and forth is an operation of order 2. It's a reflection. But rotating all three channels in a cycle is an operation of order 3.
You have it perfectly.
It's the 2 and the 3 again, the minimal 2-3 motif from the hyperbolic triangle.
Yes. The paper identifies this S3 symmetry as the minimal non-abelian relational kernel.
Non-abelian.
Non-abelian simply means that the order in which you perform the operations matters. If you swap A and B and then rotate them, You get a different result than if you rotate them first and then swap them.
Okay, order matters.
This property is crucial for generating complexity. The simple 2-3 geometric motif acts as the seed from which infinite structured complexity can grow.
How does that seed grow into the physical universe? The paper maps out a connection between this S3 symmetry and something called the Weyl group of the A2 root lattice.
Another dense term.
Before we talk about what that means for physics, break down those terms for me. What is a Weyl group and what is an A2 root lattice?
Let's start with a lattice. A lattice is basically a repeating grid of points, like a crystal structure. The A2 root lattice is a very specific two-dimensional grid.
A 2D grid.
If you look at the points immediately surrounding the origin in this lattice, they form a perfect planar hexagon. 6 points arranged in a hexagon around the center.
Okay, got the hexagon.
The Weyl group is essentially the set of symmetries of that lattice, the ways you can reflect and rotate that hexagon so that it still looks exactly the same. And the mathematics of those reflections and rotations of the hexagon perfectly match the S3 symmetry we just discussed.
Okay, so we have a mathematical hexagon generated by our 2-3 motif. Where does physics come into play?
This is where the paper jumps directly from abstract geometry into the heart of quantum mechanics. Consider the strong nuclear force.
Which binds the nucleus of an atom together.
Exactly. This is the fundamental force of nature that binds quarks together to form protons and neutrons. Without it, atoms couldn't exist. The mathematics that govern how quarks interact via the strong force is dictated by a symmetry group called SU3.
So SU3 is the mathematical rulebook for the nucleus of an atom.
Correct. Now, physicists study something called the adjoint sector of SU3 to understand the force carriers, which are called gluons. The adjoint sector of SU3 is 8-dimensional.
8 dimensions.
Back in the 1960s, the physicist Murray Gell-Mann famously called this the eightfold way, and he won a Nobel Prize for it. But geometrically, if you break down those 8 dimensions of the strong force, they don't just sit in a random clump. They break down precisely into 2 plus 6.
Wait, does the 6 correspond to the points of our A2 hexagon?
Yes, it does. In the mathematics of the strong force, those 8 dimensions are made up of 2 internal Cartan axes, which mathematically represent the pure, silent, coherent core of the system, plus the 6 root directions.
And the roots are?
The roots represent the actual interaction channels where the force is exchanged.
Yeah.
And those 6 interaction channels are arranged mathematically exactly as that planar to text hexagon.
That is absolutely staggering. So Ramanujan's coherence to symmetry to law pipeline is entirely literal.
Completely literal.
He wasn't just doing abstract theoretical math for the fun of it. The structural constraints he was exploring, the 2-3 hyperbolic geometry, the S3 symmetries, they form the exact architectural blueprint of the standard model of particle physics.
Blueprint is the right word.
He was writing down the foundational mathematical grammar that dictates how quarks bind together in the real world decades before physicists even hypothesized that quarks existed.
The thesis is that he was mapping the underlying ultimate symmetry constraints of reality. When you map the structural constraints of the universe perfectly, the physics inevitably has to follow.
It has no choice.
Because physics, in this view, is nothing more than the localized physical expression of those geometric constraints.
And according to the infographics and the paper, this structural constraint reaches its absolute peak of perfection at a very specific mathematical threshold. Here's where it gets really interesting. I want to dive into what is arguably the most mind-blowing part of the deep dive. The magic number 24.
It is a number that keeps theoretical physicists and pure mathematicians awake at night.
The sources identify 24 as a closure threshold. What does that mean? Why is a 24-dimensional space so fundamentally different from a 23-dimensional or 25-dimensional space?
In mathematics, as you increase the number of dimensions, the geometric rules change. You can build certain shapes in 3 dimensions that simply cannot exist in 2 dimensions.
Makes sense.
When you reach exactly 24 dimensions, a mathematical miracle happens. It is the first mathematical rank where 3 incredibly strict, highly specific conditions manage to coexist perfectly.
And those are?
Self-duality, evenness, and a rootless background.
I want to focus intensely on that last condition, the rootless background, because the paper heavily emphasizes a specific structure called the Leech lattice that lives in this 24-dimensional space. We talked briefly about lattices being like grids or crystal structures. But what makes the Leech lattice special, and what does it mean for it to be rootless?
Let's use a physical analogy. Imagine a greengrocer trying to stack oranges in a box.
Okay, stacking fruit.
They want to pack as many oranges into the box as possible, minimizing the empty space between them. In three-dimensional space, there is a known optimal way to pack spheres, which is how greengrocers intuitively stack fruit. Mathematicians call this the sphere packing problem.
Sure.
Now imagine trying to pack hyperspheres in higher and higher dimensions. The mathematics gets incredibly complex. But in exactly 24 dimensions, there is a way to pack spheres that is impossibly dense and perfectly symmetrical.
And that's the Leech lattice.
That specific arrangement of points is the Leech lattice.
Okay, so it's the ultimate 24-dimensional fruit stack. But what about the roots?
In lattice theory, a root is defined as a vector, a line connecting 2 points in the lattice that has a specific short length. Technically, it's called a norm-2 vector.
Norm-2 vector.
Most lattices, like the ones we can visualize in lower dimensions, are full of these short roots. In the context of mathematical physics, roots are deeply associated with activity.
Activity.
They correspond to low-energy gauge bosons. They are the mathematical triggers that cause symmetry to break, forcing interactions to happen.
So roots are like static, they are noise. They are the friction that causes the perfect symmetry of the universe to degrade into messy physical interactions.
That is a brilliant way to conceptualize it. Roots cause the system to do something. But here is the miracle of the Leech lattice. It is entirely rootless.
No roots at all.
Despite being incredibly dense, the points are arranged in such a way that there are absolutely no norm-2 vectors. Because it is rootless, it contains no mathematical noise. It completely prevents premature symmetry breaking.
It's perfectly quiet.
It acts as a perfectly quiet, pure, coherent, saturated geometric vacuum. In the framework of ontological mathematics we've been discussing, the Leech lattice represents the ultimate blank slate of reality.
The bottom layer.
It is the perfect, unblemished coherence layer before any laws of physics are generated.
And yet, from that perfect 24-dimensional silence, the most insane, massive mathematical object in existence is born. The paper maps out a progression that it calls the Moonshine pipeline.
The Moonshine pipeline, yes.
I want to walk the listener through this step by step. Let's trace how the universe gets built from the ground up. Step 1 is the coherence layer.
Right. Step 1, you start with the perfectly quiet, rootless Leech lattice in 24 dimensions. It is the unperturbed substrate.
Step 2, the paper says you apply a mathematical operation called an orbifold closure. It describes this as a Z2 involution. I need an analogy for this. What are we doing to the lattice?
An involution is an operation that, if you apply it twice, brings you back to where you started, like multiplying by -1 and then -1 again. Geometrically, you can think of the orbifold closure as taking this infinite 24-dimensional lattice and carefully folding the space over onto itself, much like folding a massive sheet of origami paper.
Holding space.
By folding it, you are identifying certain points with other points, forcing the space to close in on itself and complete its structure.
Step 3. This folding process generates an entirely new, deeply complex algebraic space called the Moonshine module.
Yes.
And the ultimate overarching symmetry that governs every possible movement and transformation within that Moonshine module is something called the monster group.
The monster group.
I have read about the monster group before, and it honestly sounds terrifying. Just how big is this symmetry group?
The monster group is the largest sporadic simple group in all of mathematics. To give you a sense of its scale, symmetry groups are measured by the number of elements, or distinct operations they contain.
Right.
The number of elements in the monster group is roughly 8 times 10 to the 53rd power.
For the listener, let's put that in perspective. 10 to the 53rd power. That is more elements than there are atoms in the entire Earth. It might be more than the atoms in Jupiter.
It is an incomprehensibly vast structure. Yet it is completely exact and fundamentally indivisible. It represents the maximum possible symmetry that can exist within this mathematical framework.
So it's the peak.
It is the peak of the symmetry layer in our pipeline.
Which brings us to step 4. The pipeline moves from coherence to symmetry to law. The interaction between the Leech lattice and the monster group produces a tangible mathematical law.
Tangible law.
And that law takes the form of the normalized J function. This is where the story comes full circle, right? Because the J function is a modular function. It's exactly the kind of function Ramanujan spent his life studying.
He explored the mathematical landscape of functions exactly like the J function. He intuitively understood the language of these curves. And the profound connection between the continuous curving geometry of the J function and the massive discrete algebra of the monster group is what mathematicians playfully call monstrous moonshine.
Explain monstrous moonshine to me. Why was it considered so shocking?
When you take the normalized J function and you expand it out into an infinite series, which is a standard way of writing out a complex function as a string of added terms, You get a sequence of coefficients.
Just a sequence of numbers.
The first non-trivial coefficient in that sequence is the number 196,884.
Just a large, seemingly random number. A local detail constrained by the global rule.
Exactly how it appeared to mathematicians for a long time. It was just an artifact of the calculation. But in 1978, a mathematician named John Mackay noticed something seemingly impossible.
What did he notice?
He pointed out that the number 196,884 is exactly 1 plus 196,883.
I have to stop you. Why does that specific addition matter? Why is that not just numerology?
Because it bridges two completely different worlds of mathematics that we're not supposed to touch.
Two different worlds.
The number 1 is the exact dimension of the trivial representation of the monster group. And the number 196,883 is the exact dimension of the smallest non-trivial representation of the monster group.
That is absolutely mind-blowing. Let me make sure the listener is grasping this. You have an analytic modular function, a curving, continuous line graph on one side of mathematics.
Yes.
And its numerical coefficients perfectly, exactly match the internal algebraic dimensions of this unimaginably massive discrete symmetry group on the complete other side of mathematics.
Yes. The paper refers to this as a literal spectral line equation.
Spectral line.
In physics, when you heat up an element like hydrogen, it emits light at very specific exact wavelengths, creating a barcode of spectral lines. Those lines tell you the internal quantum structure of the atom.
The chemical fingerprint.
The paper is arguing that the J function acts the same way. The coefficients of the modular function are secretly encoding the spectral laws of the monster group's highly organized algebraic state space.
So the math itself is emitting a spectrum.
The function is the DNA readout of the universe's ultimate symmetry.
And this brings us to the final and perhaps most consequential layer discussed in the sources, the law layer, and how modern physics is finally, decades later, catching up to the things Ramanujan was perceiving in the 1910s.
It took almost a century.
This is the part of the deep dive that genuinely gave me chills. The profound realization that Ramanujan was effectively mapping the foundational mathematics of quantum physics decades before quantum physics even existed as a field of study.
It's hard to even comprehend.
I want the listener to really internalize this. Imagine someone discovering the detailed structural architectural blueprints to a massive, complex skyscraper, 50 years before the architect who designed the building was even born.
That's a great way to frame it.
That is what Ramanujan did with the universe. Let's look at the connection to string theory because the paper highlights this as the most glaring example.
It is the most direct physical translation of his work. Let's look at bosonic string theory.
Bosonic string theory.
This is a theoretical framework that attempts to model the fundamental particles of the universe, not as microscopic dots, but as tiny vibrating strings of one-dimensional energy.
Strings of energy.
For the mathematics of bosonic string theory to be consistent, for the equations to balance and be free of mathematical anomalies that would break the laws of physics, the theory dictates that the universe must have exactly 26 space-time dimensions.
26 dimensions. But wait, we just spent 20 minutes talking about the magic threshold of 24. We talked about the 24-dimensional Leech lattice. How does 26 fit into this?
This is where the physics perfectly mirrors the mathematical constraints we've discussed. A string vibrating in space has 2 degrees of freedom that are considered unphysical in the math.
Unphysical.
Essentially, these 2 dimensions are required to define the string's own internal world sheet, its own localized time and spatial extent. They don't contribute to the physical vibrations we would observe as particles.
So you have to discard them.
When physicists subtract those 2 unphysical dimensions from the 26 total dimensions of space-time, they're left with exactly 24 transverse vibration modes.
The magic number.
The exact number. Those 24 transverse modes perfectly match the 24 dimensions of the rootless Leech lattice.
Unbelievable.
And here's the ultimate connection. This exact dimensional count of 24 is what allows modular partition functions, the very same mathematical functions that Ramanujan dedicated his life to, the formulas with the square root of n in the exponent, to behave cleanly and consistently when applied to string theory.
It's a perfect fit.
The math of the universe literally requires the 24-dimensional threshold to function without tearing itself apart.
That is incredible. And the paper makes it clear that his footprint doesn't stop at string theory. Think about something as massive and incomprehensible as black holes.
Black hole thermodynamics is one of the most complex fields in modern physics.
And Ramanujan's math applies there too.
Yes. And it is entirely dependent on the concept of counting states. Physicists need to calculate the entropy of a black hole, In quantum mechanics, calculating entropy means you have to count the massive, nearly incomprehensible number of quantum microstates that exist inside the black hole's event horizon.
But how do you count something you can't see that is hidden behind an event horizon?
You use the math of partitions.
Partitions again.
To do that counting, modern physicists use Ramanujan's exact partition asymptotic expansions. His formulas, generated in the 1910s to calculate how whole integers break down into smaller parts, are the exact mathematical tools used today to count the quantum states of black holes.
That's just beautiful.
The geometry he perceived maps perfectly onto the densest objects in the universe.
And then there is the ultimate mystery, which the paper touches on toward the end, the Mach theta functions.
The Mach theta functions.
Ramanujan discovered these functions on his deathbed in 1920. He wrote a final, now famous letter to Hardy saying he had discovered something mysterious that behaved almost like the modular forms he usually studied, but not quite. For nearly a century, nobody in the mathematics community fully understood what these functions were or what they applied to.
They were a profound enigma. But today, the mystery is largely solved. Mathematicians now understand Ramanujan's Mach theta functions as something called harmonic mass forms.
Harmonic mass forms.
Conceptually, what they represent is broken modular symmetry.
Broken symmetry.
Remember how we discussed that pure symmetry must break for a physical universe to exist? Ramanujan was mapping the math of that breaking.
He saw the break.
And today, physics relies heavily on these exact functions. They're used in conformal field theory, they're used in developing models of quantum gravity, and they are essential in calculating the topological invariance of three manifolds. Ramanujan, in his final days, was literally writing down the mathematics of broken symmetry, which is the exact mathematics of our observable physical universe.
So what does this all mean? We have covered an immense amount of ground today, from high school proofs to the monster group. But I want to bring it back to the listener. What does this mean for you and me as people living our lives, walking around in this universe? If we synthesize the paper's thesis, what is the grand takeaway?
If we fully embrace the ontological framework presented in these sources, it means that Srinivasa Ramanujan's mind functioned at the exact razor-thin boundary where global, hidden mathematical coherence yields to symmetry, and where that symmetry yields physical law.
Right.
The physics regimes we observe every day, the Newtonian world of apples falling from trees, the relativistic world of planets orbiting in cursed space-time, the microscopic quantum world of probabilities and quarks, they are not disparate, unconnected phenomena.
They're all connected.
They're just different stress levels, different localized physical expansions of this one underlying perfect geometric substrate.
So the universe isn't just described by mathematics. We are literally living inside the math he perceived. The universe is the math.
That is the ultimate ontological reality these sources propose. Ramanujan didn't invent his complex identities. He observed the necessary, unavoidable consequences of the universe's foundational geometric constraints.
What an unbelievable journey this has been. To think about a largely self-taught genius sitting in Madras, India, intuitively perceiving numbers as his personal friend.
That's really a genius.
And tracing that intuition through the negatively curved hyperbolic modular surface into the perfectly quiet perfection of the 24-dimensional Leech lattice, up through the incomprehensible scale of the monster group, all the way to Monstrous Moonshine string theory and the quantum entropy of black holes.
It's breathtaking.
It completely rewires the very definition of human genius. It shows us that mathematics is truly a discovered landscape of pre-existing realities, not just a language we made up.
It is a deeply humbling perspective on the limits of standard human cognition and the profound, almost terrifying beauty of the architecture of nature.
It really is. And I want to leave you, our listener, with a final provocative thought to mull over as you go about the rest of your day. It builds on everything we've unpacked in this deep dive. If our physical universe, with all its tangible forces, its matter, and its 24-dimensional string vibrations, is perfectly dictated by the symmetry defects of the Leech lattice and the angles of a hyperbolic modular triangle,
Yes.
are we simply living inside one specific, localized mathematical expansion frame? Are we, and everything around us, every star and every person, just the physical, tangible manifestation of a single Q-series unfolding at the infinite cusp of a modular surface?
It is, without a doubt, the ultimate question of existence.
Something heavy to think about while you're commuting or waiting in line for your coffee? Thank you so much for joining us on this deep dive. Keep your mind open, keep questioning the nature of reality, and keep exploring the hidden structures around you.